Um, so good morning, everyone. My name is Mustafa. My name is Mustafa Ismail. I'll be your instructor for Physics 401 this semester. I'm a PhD student here at UNH, PhD candidate in my 5th year. Hopefully, gonna graduate this next summer. So let's get started with the syllabus of the class to address some logistics and some things we need to have in common before we get started. So this class is 5-week long. It's very fast-paced, very fast-paced. So we're gonna find ourselves rushing at some points, but we're gonna try to maintain as humanly possible pace as possible. So the class time will be Monday, Wednesday, 2 hours from 8 to 10, from 8:10 to 10. And Tuesday to Thursday is going to be from 8 to 11. Usually we're going to have the labs and activities and worksheets and stuff on these longer days when we have 3 hours and not 2 hours. All our meetings are online. This class is completely online. And it's going to be through Microsoft Teams. The link is in the syllabus here. This is my email. If you want to ask any questions or you have anything you want to ask about the structure, anything you want to ask about the subject itself, any questions in general, you can email it to me. But please start your emails with the course code so I can filter through them quickly and get back to you as quick as I can. Okay, so I'll let you guys read this on your own, but there are a couple of points I want to stress on. First, the topics covered in this class. So this is algebra-based, not calculus-based. So the background needed from you is going to be high school level algebra and trigonometry. You will need those like identities, sine, cosine, tan, sine squared plus cosine squared equal 1. This kind of stuff. And algebra, you know, manipulating algebraic equations, dealing with symbols, solving the quadratic equation. So this is the level we're talking about. Of course, we're gonna address that when it comes naturally in the class, but this is the base we're expecting. The topics we're covering are mainly 5 topics. We're gonna start with kinematics, which just deals with motion, distance, speed, acceleration, etc. And then we're gonna discuss forces and Newton's second law, Newton's laws in general. This part deals with what causes the motion in the first place. So in the first part, we're going to discuss motion, and then in the second part, we're going to discuss what causes this motion. So this way we have cause and effect. Then we're going to move to work and energy, which essentially is the same content as Newton's second law, but manipulated in a different way to give us more understanding and more intuition about the phenomena, and some problems become easily solvable when you work in this framework instead of doing forces. We're then going to introduce momentum, and at the very end, we're going to introduce fluids. Actually, these two should be reversed. Momentum is first, and then work and energy second. But anyway, these are the topics. It's going to be a studio style class, which means everything is inside the class. So labs are inside the class, group activities are inside the class, problem solving inside the class, and then it's going to be interactive. So I will separate you into groups, and I will assign you problems, and through these problems you will learn and then get feedback instantly and so on. So it's not the classic style of lecture and then you go home and study and then come back for a lecture. No, it's more interactive. Of course, you're still expected to have homeworks and exams, but in class there are more interactions. Okay, because this class is online, all quote unquote experiments and labs will be online as well. So we will use software simulations. When I get the license this week, I will tell you what it is and how to use it. But for now, just know it's going to be online, all online. Okay. For office hours, I will have half an hour after every class, so 4 times a week, Monday and Wednesday at 10, and Tuesday and Thursday at 11. So overall, I'm going to have 2 hours a week worth of office hours. And of course, if you have extra questions, you can ask me by email. Okay, the text we're using is College Physics, the 12th edition by Survey. This is the main textbook we're using. It's available through Cengage, which is on Canvas as well. You can click the link on Canvas and it will take you there right away. This is the main text we're going to using. It's a great text. There is also another great text, which is College Physics by Night. It's not required to read it, but it's very helpful and it's a very good book if you want an extra book. But if you don't need it, you can just read Survey. Okay. The components of the class are homeworks. I need to see if yeah, I need to admit people. Okay, so as I was saying, the components of the class are homeworks, group works and group activities, virtual lab experiments because all class is online, so we're doing everything virtually, and exams. Homework is 30%. In-class group activities are 15%, and most of you guys will get these 15% because it's just for participation. It's not for accuracy. This is how you learn the material in the first place. You get introduced to the topic, and we work through it together. So these 15% are just, you're going to get those. And same for lab experiments. For exams, we're going to have 3 exams. These will be graded for accuracy. But we're not going to have them equal weights. So the highest grade for your exams will be 20%. The lowest grade will be 10%, and then the intermediate grade is going to be 15%. So overall, you're going to get 45% worth of exams. Okay. If I assign you homeworks that are not online through Cengage or WebAssign, please try to submit them as PDFs and not as images. Like, try to combine them into a PDF file so it makes it easy for me to grade. Or at least have the images clear and well written so I can understand what you're writing. Okay, as I was saying, this is a 5-week-long course, so it's very fast-paced. You should expect to spend about 10 hours per week outside class, like reading, doing homework, watching tutorials and stuff, just to get familiar with the subject. And algebra and trigonometry are very important. So if you're feeling rusty at these areas, try to spend a little bit more time or come to my office hours and we can discuss that. Okay, good. You can read through the attendance and participation and stuff. I don't require attendance, but it's strongly encouraged because of the interactions. But again, it's not graded, it's not required. Just try to attend as much as possible. Okay, we discussed homeworks. And in-class group work, these will come naturally when we assign some virtual lab experiments and exams. Okay, so this part is new because, you know, AI is new. But this is important. So I cannot realistically expect you not to use AI tools because I use them, so everyone uses them. So you can use them, but try to use them responsibly. So the rule of thumb is if it's helping you learn, then great, use it. But if it's doing the work for you, then this is gonna come back and bite you later. Either on the exams, which is the least of your worries when you graduate and face these problems later. But in general, you don't want to get a grade in class and then understand nothing about the class. That's not the point. So I expect you to be responsible when using AI. Just try to use it as a tool to help you learn, but not to do the homework for you or do the assignments in general for you. Okay. You're allowed to collaborate on homeworks or activities or anything, but when you submit something, it must be your own. So uh, you don't submit just one thing for group. No, you don't copy others' work. Again, no. You're collaborating, but you're submitting your own work because I need to make sure that you understood what you covered. Good, okay. All of these are fine. Okay, then you can read through the detailed syllabus later. Let's see. What else do we have here? We have the schedule. Let's go through it quickly. So this is a concise schedule, and there is a detailed one here. So we're gonna just look at the concise one. So again, 5 weeks. Ideally, each week will cover a unit, and then for this unit, we're gonna have an exam. But the last exam, for example, covers a couple of units, not just one unit. And they're separated differently. So lucky for us, we're not losing many days due to holidays. It's only one day on the Memorial Day, but otherwise, we're in good shape. So we're gonna have 5 homeworks, 3 exams, and in between, we're gonna have labs and problem solving and stuff. Okay, any questions before we get started in the actual content of the class? Okay, if there's no questions, let's get started. Unfortunately, I don't have the separate camera for today. So we're gonna be using my laptop camera, which means when I flip the laptop now, you're gonna be looking at the ceiling. But let me first open notes. Sharing my screen. Okay, can you all see the page here?
Yes.
Okay, I see a raised hand. Oh, okay, good. Just, okay. Okay, let's get started. So this is lecture 1. So the outline for today is the following. We're gonna first introduce what physics is, like a very general introduction. And then we're going to discuss kinematics. So for kinematics, we're going to introduce coordinate systems, and then we're going to introduce the basic language we need for discussing motion. So that will be displacement, distance, speed, velocity, and acceleration. Okay, let's see if... okay, for the introduction part, we're going to discuss the units and physical quantities. Okay, so this is for today. It's going to be brief before we get into the subject really tomorrow. But today we just need the language we're going to use later. Okay, good. So I think we all agree that the natural world around us is overwhelmingly complex. So we encounter a lot of phenomena every day, like we encounter heat, light, electricity, magnetism, biological processes, chemical reactions, and many others. And this overwhelmingly complex structure is not expected beforehand to be simple. But surprisingly enough, one of the lessons that we learned by studying physics and gathering data all over the centuries is that a relatively small set of principles can explain this wide range of phenomena. Like we will have some basic rules, and these basic rules apply to everything. So more importantly, we can make predictions. And these predictions, we can then go and test them experimentally, so it's not just guesses. We quantify our predictions, and then we go make measurements, and then we get more faith in our set of principles. So this is the general this is the general procedure for doing science, and that's what makes physics a branch of science, because again, it's an experimental subject. It deals with observations, hypotheses, and making theories, and then experimenting with them and verify them. Okay. So sorry. So physics is an experimental science, and it is concerned with the most basic ingredients of nature. So it is dealing with matter, energy, space, and time. And that's it. That's all there is to physics. It simplifies all the ingredients of nature and just deals with the motion and transfer of matter and energy in space and time. So it is the simplest of sciences. That doesn't mean it's the easiest, because it's certainly not, but it's the simplest. As you increase complexity, you then go to chemistry, and then you go to biology, and then complexity increases. But physics gets everything to the simplest possible structure. So physics asks how objects move, how forces act, how energy is transferred, and how physical systems behave from microscopic to astronomical scales. Um, physics also has lots of applications. So, for example, in life sciences, which is something we're concerned with in this class, um, the flow of blood involves pressure and fluid mechanics. Hearing involves waves. Vision involves optics. And then you have heat transfer when you measure body temperature, and also medical technologies like X-rays, MRI, ultrasound, etc. All of these are applications. But that's not what we're doing in this class. This is just the general motivation. What we're doing is motion, simply, and we're going to start with kinematics. So kinematics asks the very simple question of where is an object and how does its position change with time? So kinematics. So where an object is and change over time. So these are the two main broad questions. Okay, but before going there, we need to define what we mean by these things. So in general, to have a meaningful discussion, we need to define our terms. And that will be quick. We will define what we mean by physical quantities. We will define what we mean by units. We will define what we mean by measurement. And then we will go into the details. So let's start from the very beginning and discuss what physical quantities are. So, so a physical quantity is a property of the system. Okay, it's a property that can be measured or calculated. We're not just talking qualitative description, we are talking quantitative description as well. So a physical quantity is a property of the system that can be measured or calculated. Examples of physical quantities are length, mass, temperature, velocity, acceleration. All of these are physical properties, physical quantities, and all of these are measurable quantities. But then there is a broad distinction between the two. We have fundamental quantities and we have derived quantities. So these physical quantities can be divided into fundamental quantities and derived quantities. Fundamental quantities are those that are defined by how they are measured. So you just define a practical procedure. You cannot break them into smaller things. So these are defined by how they are measured. For example, you have length is a fundamental quantity. When you talk about length, you talk about how things compare to each other. You take a meter stick and you say, okay, this is going to be my standard, and I'm going to compare everything to it. And that will mean this object is long, this object is short, and long and short is compared to the standard that I've chosen. There's also time. Time is also a fundamental physical quantity. It's not derived. And the way we think about time is also operational. So, for example, you pick a physical phenomena that keeps repeating. Let's say a pendulum. A pendulum is swinging back and forth, and you pick one swing and say, okay, I'm going to call that 1 unit of time. I'm going to call that a second. And then when it swings twice, then 2 seconds have passed, and so on. Or you can look at the sun, and when the sun goes back to the same position in the sky, you say, okay, a day has passed. So it's operational definition. So this is what we mean by fundamental quantities. Their definitions are operational, how they're measured. Also, there is mass. It is, again, defined in the same way by measuring how objects resist motion. When you try to accelerate an object or you try to stop an object, how difficult to do that is measured by its mass. And then there is derived quantities. Derived quantities are defined in terms of the fundamental quantities. So, for example, so let's see first. So these defined in terms of other physical quantities. So, for example, we have speed. Speed is not fundamental. Speed is length divided by time. So, two fundamental quantities, and then you relate them to one another in some way to get a new quantity that will be useful in quantifying your system. In the same way, there is acceleration, which is also not fundamental. It's derived because it is how velocity changes over time. There is also momentum, which is something we are going to cover later. But momentum is defined as mass times velocity. So it's a fundamental quantity times another derived quantity. But at the end, you should be able to get a derived quantity and decompose it into the fundamental quantities it's made of, in terms of units, that is. So acceleration will be measured in meter per second squared. So that's length divided by time divided by time. Again, momentum is going to be mass times length divided by time, and so on. So the fundamental quantities are there all the time. Okay, now that we have physical quantities, we need to measure them. And to measure these physical quantities, we need units. So let's first define what we mean by a measurement. So a measurement is a comparison. That is really as simple as that. It's a comparison. It's a comparison between two physical quantities of the same type. Between two physical quantities of the same type. So again, it relies on the definition of a physical quantity, which we just discussed. And it has to be the same type. So it's a comparison, and you cannot compare things that are not of the same type. So that's why it has to be of the same type. So you cannot compare a length to time or an acceleration to mass. So you have to be, apples to apples. In principle, we can choose any unit to make a measurement. again, it's a comparison. So you can pick anything as your reference, anything as your standard, and then measure everything else in terms of it. So for example, I can pick my cup of coffee and say, okay, that makes for a good unit for length. And then I have a stack of cups and put them one on top of the other until I get like 15 cups or something, and then I stand next to them and say, oh, I am 15 cups of coffee tall. That's a perfect measurement, but it's absurd. So it's valid, but it's not useful in any way. So to do something that is useful and to communicate measurements between people and between scientists, we need standards. We need to standardize our units. So the standard system of units we use is the international system of units. The standard system of units is SI. I think SI comes from the French word for it, Sistema Internazionale. But SI units, those are the units we're going to be using. And you can convert back and forth from the international system of units. This is also known as the metric system. Metric system. Here in the US, for example, you don't use the metric system. You use the English system or the imperial system. But that's not used as often in science. So we're going to be sticking to the metric system. So in this system of units, we have, for example, length is measured in meters. And the symbol we use for that is just lowercase m. Time is measured in seconds. And we use S for that. Mass is measured in kilograms. That's kg, kilograms. And then temperature is measured in Kelvin, but we're not going to talk thermodynamics in this class, so I'm not going to bother writing it. But these are the basic units we're going to be using. There are, of course, different units. For example, you have, instead of meters, you can use feet, you can use inches, you can use miles. And instead of kilograms, you can use pounds. And there are conversions between these different units. So the reason why the metric system is nice for doing physics or for doing science in general is that it's base 10. So to go from one scale to another, you just multiply by factors of 10. For example, let's take the meter, for example. So you have meters, and then you have kilometers. Then let's say you have millimeters. You have back there, you have micrometers. And even further, let me take this here. There is also nanometers. So to go from one to the other, you just multiply by factors of 10 or divide by factors of 10. So from kilometer to a meter, you divide by 1,000. And from meter to millimeter, you again divide by 1,000. And from millimeter to micrometer, you divide by 1,000. From micrometer to nanometer, you divide by 1,000. And there is also centimeters, which you get from meters by dividing by 100. So it's always factors of 10. So the prefixes we use for that, these are going to be standard, and we're going to use them a lot. So the prefix and the factor. Okay. Let me also include the symbol used for it. So we use the prefix kilo. This means thousand. It comes, I believe, from Greek, and it means thousand. The symbol we use is just K, and it's a factor of 10 to the power 3, which is the same thing as 1,000. So, for example, kilogram, kilometer, kilojoule, all of these are units that are we going to use. There is also centi. This is the symbol C. It's a factor of 10 to the negative 2 of the original unit. So that's the same as 1 over 100. So when you say centimeter, the prefix centi, this means it's just a meter divided by 100. So 1 meter divided by 100. So it's 1/100th of a meter. We have milli. We use lowercase m for that, and it's a factor of 10 to the negative 3. Then we have micro. We use the Greek letter mu for that, 10 to the negative 6. We have nano, and that's just the lowercase n, and it's 10 to the negative 9. You can check those. We're going to be mainly using kilo and centi for this class, but just in case, if you encounter something else, you know how to convert from one to the other. Good. So we just said that we have different systems of units, and we need to convert from one to the other because all of them are equally valid. We said some of them are more useful, but again, you will encounter sometimes the use of imperial units, and you need to convert them to metric system. So we need to know how to do that. So unit conversion. Okay. So let's say we are converting length. Okay. So length, let's say we have a car. Okay. This car has a fixed length. It's this length. Whatever that is, it's just a physical length. It has some extension in space. If I measure this car by meters, or measure it by inches, or measure it by kilometers, or measure it by nanometers even, it's still the same length. The object itself didn't change. The length didn't change. So let's say this car was, let's say 2 meters long. And I want to describe that in terms of feet. How long in feet? I need a conversion factor to let me go from meters to feet. And I just forgot what this conversion factor is, so let me Google it really quick. Meters to feet. Okay, so 1 meter is equal to 3.28 feet. Okay, this is just a relation between different descriptions of the same length. If I have a meter stick, it has the same length, but I can describe it using a system of meters or a system of feet. If I describe it using a system of feet, it is 3.28 feet long. If I make it itself the standard, then it's 1 unit long. So this will be a conversion factor because I can say, okay, 1 is equal to 3.28 feet divided by 1 meter, right? I'm dividing a length by length, so the unit cancels and I get a dimensionless ratio. So this is equal to 1 because I'm dividing the length by itself. But I can use that to say, okay, 2 meters is equal to 2 meters times 1, right? And then I can replace this 1 by the conversion factor. So that becomes 2 meters times 3.28 feet divided by 1 meter. I can then cancel the meters. I can treat the units as algebraic quantities and cancel them from the numerator and denominator. So I only get 2 times 3.28, so that's 6.56 feet. And then I converted my 2 meters into 6.56 feet. Again, the car didn't change its length. It's the same length. I just used different description of the same physical quantity. So this relation here is a conversion factor. So different conversion factors are, for example, 1 mile is equal to 5,000 and something feet. 1 foot is 12 inches. 1 inch is 2.54 centimeters. So I will be giving you this when I ask you to convert from one unit to the other, or at the very least, you will have to Google it. But these are standards. So you just want to go from one unit to the other, you multiply by a conversion factor, but you rearrange it quickly. So you rearrange it properly. So let's take a couple more examples. Let's try to convert miles to meters. Okay, so example, miles to meters. Let's say I have 15 miles. Let's say L is some length equal to 15 miles. And I want to ask, what is L in units of meters? And I gave you this conversion between units. 1 mile is equal to 5,280 feet. There are more straightforward ways to convert, but let's say I just gave you this particular conversion factors and you're not allowed to use any others. And 1 feet is 1 foot is 12 inches, and 1 inch is 2.54 centimeters, and 1 centimeter is, 100 centimeters are 1 meter. And I want you to use these conversion factors to get that length in meters. It's the same thing. We're going to use conversion factors, but we're going to use them many times. So L is equal to 15 miles. Those 15 miles are 15 miles times 1. But this one I can write as 580 feet divided by 1 mile. The unit I want to get rid of, I put in the denominator so I can cancel it with the numerator. Okay, so that becomes this number. I'm not going to bother multiplying it using a calculator. It's just this number in feet. Okay, and then I want to convert from feet to inches. So I'm going to multiply by another conversion factor. So again, 1 foot is 12 inches, and cancel the units, feet. So I get this number in inches. So 15 times 5,280 times 12. That's the same number in inches. And then I convert it to centimeters. I'm exaggerating the steps so you guys can see it in detail. But when you're doing it, you don't have to do all that. You can just multiply by multiple conversion factors at once. But I'm just fully exposing it so you can see it. Again, the inches in the denominator to cancel with the inches in the numerator. So 2.54 centimeters, the inches cancel. So far, I got the centimeters, and I have to get it to meters. So 15 times all this mess, 2.4 centimeters, and I finally multiply by 500 centimeters downstairs and 1 meter upstairs. So the final unit cancels, and I get meters. 15 times 5 to 8, 12 times 2, 4 times 1 over 100. That number in meters. And I have it in my notes here. This number is 24,140 meters. Okay. And like if you want to convert it to kilometers, you just divide by 1,000. So that's 24.14 kilometers. There is, of course, a straightforward conversion between miles to kilometers. You just multiply by 1.6 to get it. But I wanted to go the long route to just expose the process in general of converting from one unit to another, just very generally. Okay. Okay, so given that, I want to give you 2 examples. So you guys do them, like take 10 minutes, and then we just verify that we are on the same page, and then move on to discuss kinematics. So let me get the exercise so you can see it. Stop sharing that and share. I want to share lecture 1. Class. Yes. Can you see the screen here? Can you see the exercise? Okay, I see a thumbs up. Good. Okay, so these 2 exercises convert the speed from kilometers from kilometers per hour to meter per second and miles per hour. And then for the second question, you convert from feet and inches to meters. Okay. The conversion factors, you can let me write the conversion factors for you. um, from yeah, so the conversion factors you have from 1 kilometer is 1,000 meters, and 1 mile is, let's see, I guess it was 1.6 kilometers, but I have to check miles, so kilometers. Yeah, 1.61 kilometers. Okay. What else? We have 1 foot is 12 inches, and 1 inch is 2.54 meter, and 1 meter is 100 centimeters. So these are the conversion factors you're going to use. And let's check if we got some answers by 9:10, so 7 minutes, and then we're going to continue.
I got 27.78 meters per second.
Okay, good. Yep. And for miles per hours,
I got 62.11 miles per hour.
that's also correct. Great job. Okay, did anyone do question 2 as well?
I got 1.85 meters.
Okay, great. Yeah, that's about right. Okay, great. Good job. I think we then move to the next part. Yeah, I need to see what's the problem with the chat, but not now. Let me share again. Okay. And okay, so now we know what physical quantities are, what a measurement is, what units are, and we can move forward to discuss kinematics. You can consider this the serious start of the class. So kinematics. Kinematics is the study of motion without considering its cause. So the word kinematics itself comes from the Greek word kinema, which means motion. It's incidentally the same word from which we get the word cinema, which again, concerned with motion, moving pictures and stuff. So that was the origin for the name. So it's the study of motion, the study of motion, but we don't care what set this motion in place in the first place. So without considering its cause, okay, we just see motion and we describe it. We don't ask why, we just ask how. The why question will come later when we discuss forces and dynamics, but we now only consider the how question, like how is this object moving? Where was it? Where is it going? How long did it take to get from point A to point B? How fast was it going in the beginning? How fast did it finish the motion? So just description, no asking why yet. Okay, so again, so it asks where, okay, when, how far, and how fast. Those are the kinematics questions. Where, this is position. When, this is time. How far, this is distance and displacement. And how fast is speed and velocity. And there is also how fast is it changing speed, which is acceleration, but I don't find the question in English for that. So, okay, so the basic quantities are position, which we denote by the symbol x, as a function of time. So we use the function notation, when you have a function f of x, where you have a machine that you give it the input x and you get output f of x, and this is the machine f. We use the same notation, x of t. So you feed it a particular time and you get as an output the position. So this gives you the position, or let's say it's where an object is at a particular time t, at a particular time t. This is the notation we use. Sometimes we have a symbol notation where we use x sub I, which means the position initially, like when the motion started, the initial position was that. So this is initial position. And we also use x sub f to denote final position. So those are just shorthand notations. And x of t is the general position at any particular time. Then motion itself, so this is the position. Now motion is the change in position over time. Change in position over time. But I kept it deliberately vague because we have two different changes of position over time. There is steady change in position over time, which describes velocity, and then there is the change of the change, which would be the acceleration. So we will get that now. And kinematics describes that. It describes the motion without considering the cause. Okay, now we have a quantity that describes where an object is, and we want to describe how that position changes over time. But to do that, we need a reference, because there is no meaningful notion of where something is without describing with respect to what exactly. So, for example, I can say I'm standing 2 meters from the right wall, or from the corner 3 meters. So I need a reference. And that gets us to coordinate systems. It's a fancy word for, a reference. So coordinate system. So a coordinate system is the construction needed to describe the position of an object. So for example, let's say there is again, there is a car here, and this car is at some location, and I want to describe this car with respect to something. So let's pick this point as the origin, which again is a fancy word for the reference point. And we call this point x equals 0, or define it as the 0 point. It's the origin. We define this point to be x equals 0. And then I choose an orientation. So I choose an axis and define that direction to be positive and the other direction to be negative. So let's choose the right direction to be positive. So this is positive. So positive going to the right and negative going to the left. This is the same thing as when we did the real line in math, when you have 0 at the origin and then you have positive numbers to the right and negative numbers to the left. We're doing the same construction here. So then the car is here at this point, and let's say this point is x equal 4, and I will need units for that. So it's positive 4, let's say, kilometers from the origin. This origin is an arbitrary point. You can choose some reference to make it your origin. Let's say we take the post office to be the origin. So what I did here is quantifying the construction. Instead of saying, oh, the car is 4 kilometers from the post office, I just did that mathematically. I put the post office at the origin at x equals 0, and the car is at x equals positive 4 kilometer. If instead the car was to the left of the post office, then this would be, let's say, x equals negative 2 kilometers. This negative sign means to the left. So positive to the right, negative to the left, and that's just a convention. It's a choice. There is nothing wrong with flipping these axes and calling the left to be positive and the right to be negative, as long as you're staying consistent. So you pick a choice and stick with it. Okay. This is for one-dimensional motion. When we get to two-dimensional motion, this construction will be a little bit more involved when we will have two directions instead of just one direction, positive and negative. And then we will need vectors, but we will discuss that later. But the same construction, we choose an origin, choose axes, and then define what direction is positive, what direction is negative. Okay. Okay, so that tells us the position of things relative to the origin. Now we know how to describe where something is. We now need to describe the displacement of something. So it was here first, and then after a while it was there. So that takes us to displacement. Again, at this stage, I'm just laying down the language we're going to be using in kinematics. Displacement. Okay. Let's draw our coordinate system, one-dimensional coordinate system, with the origin here, x equals 0. And this is positive x-axis, and this is negative x-axis. Okay. So let's say an object started here. This was x initial, and then after some time, it ended here at some x final. The displacement is this vector there, this arrow. This displacement we denote by delta x. The Greek letter delta, this is like you can read it as delta. This means change in something. So if we say delta x, that's the change in x. If we say delta t, that's the change in t. So displacement is defined as this delta x. So delta x is defined as the final position, x final, minus the initial position. Okay. Displacement can be positive or negative, depending on where you started and where you ended. Positive displacement will mean the vector is pointing to the positive x-axis, according to our definition, and negative one will be pointing to the left. So a specific example of that, let's say x initial was at the origin, x equals 0, and x final was 2 meters. In that case, delta x would be x final is 2 meters minus x initial, that's 0 meters. So that is positive 2 meters. Another example would be going 3 meters to the left. Okay, so x final be negative 3 meters. And x initial is again 0. I'm using different colors to give different examples. So delta x in this case would be the final position is negative 3. Initial position is still 0. So that's negative 3 meters. There is nothing wrong with negative displacement. It just indicates direction. Displacement in general is a vector. And again, I will discuss in detail what a vector is when we go to two-dimensional motion. But for now, vector is just a quantity that doesn't just have a magnitude or size. It also has a direction. It tells you where you're going, not just the size of your distance or the speed. So displacement is a vector. And we denote vectors by a little arrow on top. So really, we should be having these arrows for our vectors. But usually in one-dimensional motion, we just skip those and indicate the direction with a sign. But in general, you should have all of these as vectors. Okay. Okay, so we have positive displacement, we have negative displacement, and also the initial point doesn't have to be at the origin. You can have an arbitrary vector that starts here at -1, for example, and ends at +1, and it will be a very valid displacement. You move 1 meter from the left of the post office to 1 meter to the right of the post office, and then you cover 2 meters in general. So yeah, that's the displacement. Good. Once we have displacement, we can define distance. We need to be very accurate with our terms because if you're not accurate with your terms, you're going to make mistakes, both logical and mathematical. So this distance is a scalar, is a fancy word for a number. So it doesn't have direction. We define distance as the magnitude of displacement. So we denote the magnitude by vertical lines, which is like the absolute value, but we don't really mean the absolute value because it's in 2 dimensions. We will have the vector is described by more than just positive or negative sign. So some people write 2 bars, but I'll just write 1 bar, and you be careful that it's not the absolute value, it's the magnitude. So this is the magnitude of the vector delta x. Okay. When we only have one-dimensional motion and it's only positive or negative, then it is the absolute value. So, for example, in the first example where the displacement was positive 2 meters, the distance was also 2 meters. But when the displacement was negative 3 meters, the distance is just 3 meters. Distance doesn't care what direction you went in. It only cares what's the separation in meters or in whatever unit you're using between the initial and final point. What's the distance between these 2 points? Okay, so it's the magnitude of the vector, and it's always non-negative. So delta x is always non-negative, so it's larger than or equal to 0. It can never be 0. Displacement can. It can be positive, negative, or 0, but distance, it can only be non-negative. Okay. One other related thing is total distance traveled or path length. So total distance traveled, and Survey calls it path length, which I guess is a more accurate name, path length. This is not the same thing as the distance, and it's not the same thing as displacement. This is the actual length you covered going from one point to the other, including all the detours you made, including all the wiggles, all the zigzags, not just the initial and final point. This is like if you had a meter stick with you and covered every inch you stepped, that will be your, that's like what your car reads when it gives you how many miles you covered. That is the path length. Because at the end of the day, if you go from your home to some place and then you come back home, the initial and final points are the same. So the displacement and distance are both 0. But you went somewhere and came back. So the path length cares about the details that happened in between. So this is the actual length. So let's give an example on that. Let's say, again, we have that coordinate system. We have the origin here, x equals 0. And let's say you started at x equal negative 2. Let me have this there. 1, 2, 3, 4. Okay, now we'll just number these with numbers without x's. So 0, negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4. Okay, let's say you started at x equal negative 2 here. That was your starting point. This is x initial. You went all the way to x equals 4. Okay. And then you switched gears and came back until x equals 1. So this is the final position you're at. But the actual path you've taken is this one. This long one is the actual path. In this case, the displacement is really just x final minus x initial, which would be 1, let's say this is in meters, so this is x in meters. 1 meter minus negative 2 meters, so that's positive 3 meters. This would be the displacement vector from here to here. This would be delta x. Okay, that would be only caring about the initial and final positions. And distance would also be 3 meters. But we don't ask about that now. We're asking about the actual path length, which we call d for distance. So d is really how much distance you covered. So you went all the way from -2 to 4. So these are 6 units. And then you went extra 3 units. So overall, you have 6 plus 3 meters, 6 meters plus 3 meters. So you covered 9 meters. So while displacement and distance were 3 meters in some direction, the path length itself was 9 meters. So there is a distinction between the two, which should be taken into account. Okay. So far, so good. Okay. That's all there is to know about position. The next thing we need to talk about is time. So, time. Time. Okay. So time is one of the fundamental quantities that can only be defined by how it's measured. You cannot define it otherwise. It's only defined by how it is measured. It's an operational definition. It's associated with change in physical quantities. For example, as we discussed a little bit earlier, that you get a change in the sun's position in the sky and define a day, or you use a pendulum and this pendulum swings and you define that to be your second. Any periodic motion, you pick a unit of it and define that change to be your time unit. So the meaningful quantity here is the elapsed time, not really the time itself, but the elapsed time. So elapsed time, and we denote that by the symbol, again, delta t, which means the change in time, and that is defined by t final minus t initial. T initial is the time at which you started your stopwatch. You can think of it this way. You click your stopwatch, you define that to be the 0, that's where the time starts. And T final is the time the event ends. And then the elapsed time is the difference between the two. So this is the starting time, and this is the ending time. Okay? Delta T is always positive. Time always goes forward. So the change in time is always positive. T final will always be bigger than T initial. Time doesn't stop. This is different from displacement, which could be negative or positive, but no, delta T can only be positive. Okay? This is physically meaningful, but T final or T initial, those can be negative. Those can be anything. Those can be positive, negative, or 0. That's just convention. So when we do problems, when we do kinematics problems, sometimes you solve a quadratic equation and you get 2 answers for the time. And one answer would be positive and one other answer would be negative. And then students usually make the mistake of saying, oh, time cannot be negative, so I must choose the positive time. But that's not correct. Time can absolutely be negative. It's the change in time that cannot be negative. But time itself can be negative, and we use negative times all the time. One very familiar example is to say, okay, some event happened in the year 300 BC. This 300 BC here means exactly t equals negative 300 years. This BC is the negative, okay? Because in that system we have chosen, we chose some point to be the reference. We chose some point to be the stopwatch equals 0. So we set t equals 0 to be the birth of Christ, for example. And then BC is before Christ and AC is after Christ. So before that event, time is negative. And after that event, time is positive. Okay? But the change is always positive. Okay, this is an important conceptual point because these individual labels, T final and T initial, those are conventions. But delta T is physical. Okay. Sometimes it's useful to set T initial to be 0 and you only write T as a shorthand, but I don't like to use that because sometimes it enforces the confusion. So, okay, so elapsed time, displacement, distance, we got all the fundamental quantities we need. We get to the first derived quantity. I'd like to remind you guys that all we're doing here is defining the language we're going to be working with. So let's see, we have now velocity.
We can't hear you. Wait, now we can.
Sorry, can you hear me now?
Yes.
So what was the last thing you heard?
When you wrote vector.
Oh, okay. So you didn't hear the definition of the average velocity and the. Okay. But you can hear me now.
Yes.
Okay, good.
Yes.
So what I was saying is that velocity is a vector, and we defined it as the change in position divided by the change in time. So delta x divided by delta t, that is the total displacement divided by the elapsed time. And I was saying that this 3 bars on top of one another instead of just equal sign, that just means defined as. The average velocity only cares about the initial and final positions and times. So it doesn't tell you anything about what happens in between. So for example, if you went to the grocery store and then came back to the same position, which is your home, your average velocity is 0. Even though you spent time there, you did stuff, you still have your average velocity 0. So because you came back to exactly where you started. Okay. To get more details about what happened in between, we make the time interval smaller and smaller until we make it really small, and then that gives us the instantaneous velocity. And that's closer to what your car speedometer reads. Okay, although your car speedometer doesn't read direction, so it really tells you the instantaneous speed, but the instantaneous velocity is closer to what your actual velocity is. It's instantaneous. So v instantaneous, which we just write as v without any subscripts, is the limit as delta t goes to 0. Don't worry about this notation if you don't know it. We're not going to use it in this class, but this is just the formal definition, delta t. So what this means is that we make the time smaller and smaller and smaller, so we get the velocity approaching a finite number that represents what's happening now, instead of just what happened between two different intervals. So you make it smaller and smaller until you theoretically get it to 0, and then when you get it to 0, t initial and t final really become the same point, so it becomes an instantaneous velocity instead of an average velocity between 2 points. This is the mathematical description of what I've just described. This is the instantaneous velocity. And this is average velocity. So the instantaneous velocity is the average velocity as you make the time infinitesimally small. Okay. Good. Speed or average speed, that's a scalar. So it doesn't have direction. I should have added the vectors here because that was a vector. Speed is a scalar. So the instantaneous speed is the magnitude of the instantaneous velocity. But the average speed is defined as the total distance traveled, or let's call it the path length divided by the elapsed time, or delta t. Okay. So so in the same example that we gave earlier about the going to grocery store and back, so let's actually give it as a concrete example. Let's set your home at the origin, so x equals 0. This is home. And let's set the store to be at x equals 3. And the axis here is distance in kilometers. Okay, so so let's see. So this is your initial position. This is x initial. You go to the store and back. So again, this is also your final position. So x equals 0 and x equals 0 here. So your displacement is 0. So your average velocity is 0. So v average is 0. But the average speed is not 0 because you covered 6 kilometers. So this distance is 3 kilometers overall. You went back and forth. So let's say the path length is equal to 6 kilometers. And let's say you spent half an hour going back and forth. So the delta time, delta t is half an hour, 0.5 hour. Okay. So the average speed is, the average velocity is 0, but the average speed is 6 kilometers divided by half an hour. So 12 kilometers per hour. This has a little bit more information about what happened in between than average velocity. At least it tells you that you spent some time somewhere because it gives you a number, but the average velocity doesn't tell you anything about what happens in between. All of these converge to the same numerical value when you make the time interval smaller and smaller and smaller until you essentially get it to 0. So instantaneous speed is the limit, sorry, no, it's the magnitude of the average speed. The magnitude of the instantaneous speed. So magnitude of instantaneous speed. Okay. So so different quantities tell you different things about the motion. Some quantities tell you what happened in between, more or less. Some other quantities don't tell you anything about what happens in between. And some other quantities are just defining the construction we work with. Let's not discuss acceleration today because I wanna get these things settled in first. Displacement, distance, path length, velocity, speed, all of these are going to be important when we incorporate them into problem solving. So let's just focus on this for now. And please read the relevant parts in survey about this. I'll also upload the lecture notes for today, which will cover what we discussed all the way through until velocity. I will upload it right after the class. And oh yeah, I forgot to tell you something. Today I'm going to send you a problem set that is not graded or not like it doesn't factor in any of your grade, but it's just a math assessment to tell me where you guys all are so we can tailor the discussion to the math skills you have and develop things as we go. So try to complete it by tomorrow evening. Like it's not graded, just give it an attempt. And yeah, I will assign it after class. Let me stop sharing my screen. Okay, with that, that's all I had to say for today. We covered quite a lot for a first class, but get used to the pace because it's a very fast course. Do you have any questions for me before we end today's lecture? Well, if you don't have any questions for me, just I hope you have a great day and we will meet again tomorrow.
Thank you so much.
You're welcome.
you.
Thank you.
Thank you.
Thank you.
Thank you.
Have a
Have a good one.
Guys.
Thank you.
Thanks.